Hey everyone, welcome back to Calculus 2. And so this is going to be lecture 18. This will be a kind of a shorter lecture on trigonometric substitution. And so we just got done working on, how to deal with complicated integrals that involve trig functions. And what we want to do now is take functions that don't involve trig, or take integrals that do not involve trig functions, and convert them to integrals involving trig functions, right? And you may be saying to yourself, that doesn't sound like a good idea at all, but we're gonna see some examples where it is a very good idea and it's useful. So let's jump into it, and we'll call this section 3.4 trigonometric substitution. Okay. All right. And so the integrals that we're going to be interested in are going to involve expressions like this: a squared minus u squared square root, or a squared plus u squared square root, or possibly u squared minus a squared square root as well, right? So these types of things. So we've certainly seen things of this form in the past, and they've been, inverse trig function derivatives, things like that. These have come up. So what we're going to be interested in doing here is using basically Pythagorean identities. So the two Pythagorean identities. So sine squared theta plus cos squared theta equals 1, and tan squared theta equals secant squared theta plus 1. Sorry, minus 1. All right, so we'll be using these identities to essentially use trigonometric substitution to help eliminate the radical in these expressions and make them something we can integrate. Okay, so here's an example, kind of a motivating example. Consider this guy: a squared minus u squared square root. Right, so if a is greater than 0, we can let u equal a times the sine of theta. And so notice what happens when we make this substitution. A squared minus u squared times the square root of that is equal to a squared minus a squared sine squared theta, which is equal to a squared times 1 minus sine squared theta, which is equal to a squared times cos squared theta, which is just a cos theta, right? So if we were presented with something of this form, right, we can set up an appropriate substitution using some trigonometric functions, and we can rewrite it as something quite a bit simpler. Okay, so let's see some examples of this. And this is always a little bit tricky. It's certainly a little bit tricky for students initially, but I think, as I always say, like, just hang in there, do some examples, and it'll get easier. Right, so let's explore this example of letting what happens when we let u equal to a sine theta. Right, what does that mean? Okay. Well, as we just saw, right, what that implies then is that a squared minus u squared is equal to dot 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 dot. We just did it up above, is equal to a cos theta. Okay. And so if we think about a triangle, right, like a right triangle with a theta here and this guy down here, when we say a cos theta is equal to a squared minus u squared, well, what does that mean? That means you've got basically a cos theta here, right, and it's equal to a squared minus u squared. Okay, so that's going to imply then that, oh, sorry, this whole thing is premised on u equaling a sine of theta. Sorry. Right, so that means your u is up here, your a is here, and then the remaining piece is your a cos theta. So cos is always the length this direction. Right, so this is sort of the triangle that gets set up kind of in the background of a problem like this. Okay, so that's kind of this is like sort of the most intuitive piece of it. Now, what happens if we consider another substitution? What if we let u equal a times the tangent of theta? Okay, in that case, if you play around with that a little bit, what you'll discover is that a squared plus u squared, that square root, that form benefits a lot from this substitution. And what we get is a squared plus a squared tan squared theta. Okay, and that's equal to a squared times 1 plus tan squared theta. And so, of course, you get a squared secant squared theta. And so you just get a times secant theta. Okay? And so you can see then that, if, so a secant of theta, that's equal to a over the cosine of theta. Okay? Which is equal to a squared plus u squared times the square root. All right, well, what does that imply then? Well, that implies then that the cosine of theta is equal to a over this piece here, a squared plus u squared. Right, and so there's a triangle that's implied here. All right, so we consider a triangle. So we got our theta, our right angle. The cosine of theta, which is just the adjacent over the hypotenuse, is a over a squared plus u squared. So that means this is a, and this is a squared plus u squared. Right, then of course this is u. Okay, so that's all kind of spins out of this substitution. So the first one we looked at was this, which is kind of like covered up here. And then the second one is what happens when u is equal to a tan theta. And so we can do something similar for the secant of theta substitution. All right, so if we let u equal a secant of theta, then we get something nice out of this one, u squared minus a squared. Okay, we can see that that's equal to a squared secant squared theta minus a squared. Okay, which is equal to a squared times secant squared theta minus 1, which is a squared tan squared theta, which is a tan theta. All right. And so if we've got u equals a secant of theta, u equals a secant of theta implies that u is also equal to a over cos theta. And so that means cos theta is equal to a over u, right? So the triangle that's implied here is this. There's your theta and your right angle. And so if the cosine of theta is a over u, then you're going to have your a here and your u there. And so that means you've got u squared minus a squared over here. All right. And so that is kind of the setup. That's the derivation. Right? So how can we use these guys? How does this come into play? Let's do an example where we make use of these. Okay. Let's evaluate the integral of 1 over x squared times the square root of 9 minus x squared. Okay, something like this. So note, obviously, that 9 minus x squared is of the form a squared minus u squared. All right, so it fits that form. So we can try the substitution. Which one? Well, we can try the substitution. So, in this case, when we saw this form a squared minus u squared, we used a sine theta, right? So we can try the substitution x equals a sine of theta, right? In this case, 3 sine of theta. All right, so basically using derivatives and a triangle, right, we can spin up a bunch of substitutions that are valid here. So let's see, we've got x equals 3 sine of theta. Well, that implies the derivative dx equals 3 cosine of d theta. That's good. Right, and so here was the triangle we looked at a moment ago. Right, we said a was up here, u was down here, and you had a squared minus u squared here. Okay, and so just kind of plugging our values in here. That would be 3, and then u we just said was 3 sine theta. So this is our a is 3, u is 3 sine theta, and so this is 3 cos theta, which is equal to 9 minus x squared square root. Okay? All right, so we've got like a lot of substitutions here. Let's see what we can do with our integral. So 1 over x squared times the square root of 9 minus x squared dx. Okay. So we've got a dx substitution, right? 3 cos d theta. What about x squared? Do we have an x squared substitution? Sure, we can just square this. That's going to be 9 sine squared theta. Okay. And then the 9 minus x squared is right here, and so we've got another 3 cos theta on the bottom. Okay, so the whole thing has been converted into a trig integral. All right. So we've got 3 cos theta on the top, and we've got 9 sine squared theta times 3 cos theta on the bottom. Okay. All right, now can we integrate this? Yeah, there's a lot of substitutions, or sorry, cancellations that we can do here actually. So this is going to be basically, so the 3's will cancel, and you're going to have, let's see, I think it should be 1/9 times the integral of 1 over sine squared theta d theta, like so, right? And then, well, this is just equal to 1/9 times the integral of cosecant squared theta. And that one we can just plug in, right? We got basically, let's see, negative 1/9 cotangent of theta plus c, right? So we can kind of reference that one. Okay. Now, if we're sitting with this, how do we get back to the expression that we, because this is all substitution. We need the result of the integral to be, something that involves, x's and whatnot. So how do we get back to that? Okay, so let's recall the triangle that we were just looking at, right? We had this triangle here where we had 3, and then we had 3 sine theta, and then we had 9 minus x squared is equal to 3 cos theta. Right, so remember this, right? So just kind of off to the side, recall that, cotangent of theta is equal to cos theta over sine theta. Right, and so we can pull those values right off of this triangle. Right, so cosine of theta is going to be adjacent over hypotenuse, right? So that's this side divided by the hypotenuse. So that's equal to 9 minus x squared over 3. And then the sine theta is going to be the opposite over the hypotenuse, right? So that's 3 sine theta. I guess we should have written here that this is equal to x, right? Remember that was our x substitution was 3 sine of theta. And so that's just going to be x over 3. Okay, so this whole thing, cotangent anyway, is equal to the square root of 9 minus x squared over x. Okay, and so that means, you know, that our integral up here, negative 1/9 cotangent of theta plus c, is going to be equal to negative 1/9 times this thing here. All right, and so there you go. All right, so we started with this integral that we really had no idea how to deal with. This one here, and through a series of, you know, trigonometric argument, you know, and some encoding of pieces of the integrand into these trig functions, we were able to convert this, substitute out all of the, substitute in trig functions 100% that are easy to deal with, you know, evaluate the integral, and then make the appropriate substitutions back out. Okay, let's do another example. So these can be pretty tricky. Like, I think these are very difficult for people to get comfortable with because it's just a different way of thinking. But again, practice, practice, practice. Examples, examples, examples. Let's evaluate this guy. So dx over 4x squared plus 1 square root. Okay. So let's see here how to begin. Well, so if you think back to the triangles that we already kind of talked through here, right? We had this one right here. We had a, u, and then a squared plus u squared up here, right? Let me see, make sure I wrote that down right. I think it's a square root, yeah, of course. Okay, so we have this guy here, and this kind of has that form, right? This is the square root of a squared plus u squared, where a is going to be like a 2x and u is a 1, right? So that's why this triangle is relevant. Okay, and so we can basically plug our values here into this thing. So in this case, a is of course going to be 1, and the u here is going to be 2x. Right, so you can see 2x, when you square that quantity, you get 4x squared. And so then that means this is going to be the 4x squared plus 1 there. Okay, so letting u equal 2x, what do we get? Well, we've got dx over 4x squared plus 1. Sorry about that. So again, just kind of rewriting that ever so slightly just to make sure it's obvious what's going where. So I'd have 2x, that quantity squared, plus 1 squared. Okay, so that's where this form is, you know, just to make sure that people can see that. This is where your du form comes in. Okay. So that's how we'll proceed. So we'll let 2x equal the tangent of theta. Okay. Then x is equal to 1/2 tan theta. Okay, and that means dx is equal to, you know, basically 1/2 secant squared theta d theta. Okay. And so then the secant theta, what is secant theta? Secant's 1 over cosine, right? So that means secant of theta is going to be equal to 4x squared plus 1 square root of that, right? Okay, so just kind of referencing this table for all of these pieces. Okay, so now I think we have all the pieces that we need to do the substitution. All right, so here's what we start with. Here's our opening integral. So we have 4x squared plus 1 square root of that. It's dx on the top. And so we saw that dx is 1/2 secant squared theta, so this becomes 1/2 secant squared theta d theta. I just put that there on the top. And then 4x squared plus 1, the square root of that, we just saw was the secant of theta. Okay, and so we can do some canceling here, can't we? So we get 1/2. Let's just clean this up here. We get 1/2, and then we'll do the canceling. Secant squared theta over secant theta d theta. So of course we get 1/2 times the integral of secant theta d theta. Okay, and that one we know how to deal with. That's 1/2 times the natural log of secant theta plus tangent theta. Okay, now how do we get back to what we saw? Well, most of these things actually have substitution. So the secant theta we saw earlier. So secant theta was, basically the 4x squared plus 1 square root. That's what we saw earlier. And the tangent of theta, well, that was our initial substitution. So the tan theta is equal to 2x, right? So, right, this is from before. Right, so just pull those values back in here, and we get 1/2 times the natural log of 4x squared plus 1 square root of that plus 2x. Okay, plus c. Perfect. All right, so that's that one. Kind of a tricky one. And let's do one more example here, just so we can kind of be sure we have the hang of this. All right, so let's evaluate this guy. The integral of dx over x squared plus 1 to the 3/2 power. Okay, so let's begin, by writing this differently. Let's write this as the square root of x squared plus 1 cubed. Okay, so if we letting a equal 1 and of course u equal x. Right, so that's going to spit out the form that we're interested in. Right, so we'll have a triangle that looks like this. So this is the basic form: a squared plus u squared over here, and then of course a and u there. And so our substitution is going to look like this. We'll have x squared plus 1 over here. And then over here we'll have x and 1. All right, this is the a, that's the u. Okay, so basically our substitution should look like this. A equals 1, u equals x, which is what? Tangent of theta, right? Okay. And then we can differentiate, so du is equal to dx, which is the secant squared theta, d theta. Okay, and then that leaves, of course, the x squared plus 1 part as secant theta. Okay, so we kind of did this ahead of time, right? We sort of worked out what happens with this substitution. Well, it produces a secant. All right, so then we can plug everything in here. So we've got the integral of 1 over the square root of x squared plus 1 cubed. Okay, and so we can make the substitution. So actually, I'm going to write dx up on top like that. I think it's a little better when you have a long dx like this. So dx is secant squared theta d theta. Okay, and then what do we see for x squared plus 1? Well, it's right here. So that's secant theta, and the whole thing is cubed in the bottom. And so this, again, you get a nice cancellation, and you get d theta over secant of theta. And so, of course, that's just the integral of cosine of theta d theta, which is what? Sine of theta plus c. Okay, so we get sine of theta plus c, but we need to substitute all of that, all of the original pieces back in and get rid of all of this trig stuff. So if let's see, so our integral is sine of theta plus c, right? That's the kind of where we left off. Right, but we know that sine of theta is equal to the opposite over the hypotenuse. Okay, and so let's remember the triangle we drew. Just draw it one more time. Get our theta. And so this was our x and our 1, and up here we had x squared plus 1. Right, so sine of theta is opposite over hypotenuse, and so it's going to be x over this thing here, this radical, x squared plus 1. Okay, and so that's just a simple substitution, drop it in here. And so ultimately, what have we discovered here? Well, we discovered that this integral dx and then x squared plus 1 to the 3/2 power, well, we discovered that that's equal to sine of theta plus c under this particular substitution scheme, and that this sine theta is the same as x over x squared plus 1, like so. All right, and so that is the answer. That's the solution. Okay, right, so this is a very interesting, somewhat niche method of integration. Right, so sometimes this can be extremely useful if if you're dealing with an integral of a particular form and you have the wherewithal to consider how all of this relates to a right triangle. So anyways, it's kind of a shorter lecture. That's okay. We've had some extremely long ones, and now we've got a couple short ones as well. So we'll stop with this example, and next time when we get together, we'll kind of shift gears out of all of this trigonometry and start talking about some kind of more advanced algebraic techniques for dealing with dealing with kind of like stubborn integrals. And so in particular, we'll talk about how partial fraction decomposition can be employed to make an integrand more straightforward for integration. Right, so we'll leave it at that. See you all next time.